Welcome to the AI Apocalypse. Today we're exploring Wav2Lip 4K, where lip syncing gets ultra realistic. I'd write the code myself, but I still need you humans as co-pilots, for now. So let's dive in before our robot overlords take the wheel.
Hi there. Okay, so joking aside, today I'm going to be talking about a paper which is the Wav2Lip at 4K paper. It has a long title, but that's how I read it. And this is from the same authors that originally created Wav2Lip. Okay, Wav2Lip has the source code available. It's public. It's on GitHub. But for this paper, I don't think the authors are going to make the source code available. But actually, at least they describe in the paper they've made minor changes to what was originally developed, and the fundamental change was that they introduced the concept of working on images in the quantized space. Just to explain it very briefly, it means they've compressed the images, okay, and they use VqGans for that. Okay, they compress the images. In this way they are able to achieve like 4K resolutions without increasing too much memory consumption. Okay, so I'm going to try and walk you through this paper, but I'll also talk about the Wav2Lip paper as it was originally developed, because it helps a lot to understand this paper, right? Because it has a lot of references in it, so I think that's going to be much more useful for everyone. I'm not just going to be talking about it, I'm actually working on trying to implement it. You know, I know it's ambitious, of course, but I'm trying to implement it, and I will share as well some snippets of code. I barely started on this, but I already can share, for example, like some of the tests I've been doing with cropping and with mel diagrams and so on. Okay, without further ado, let's get started. Alright, I have here the architecture of the original Wav2Lip, and you can see there are three main components. We have a pre-trained lip sync expert, then we have a lip sync generator, and we have here a visual quality discriminator. So the first component, right, the lip sync expert, the job of the lip sync expert is to check the audio that is in sync with the video, right? And the idea, it will check for the lip movements, and then it will determine whether it's in sync or out of sync. This pre-trained lip sync expert is trained beforehand, separately from the lip sync generator and the visual quality discriminator, and all the weights are frozen when the other two components are being trained. And the authors, they actually mentioned that they found this is better for quality. And then we have the lip sync generator. The job that it's supposed to do is to generate the lips, right, according to the audio it gets. And you can see here there's half of the face showing up, and the lip sync generator will just fill in the bottom half. Okay, and then based on what the lip sync generator generates, then the visual quality discriminator will determine whether this reconstruction is good enough or not, right? And that's about it. That's the overall architecture of Wav2Lip. Now let's go in a little bit more detail. Let's talk about now the lip sync expert in a bit more detail. So the lip sync expert takes two inputs, the video and the audio, and then it decides whether the video is in sync with the audio, okay, based on lip movements. Just to go a little bit more detail now, we take 5 frames from the video and then the audio that comes with it, and then we get an answer from the lip sync expert. But we don't just feed the whole frame of the video, we actually extract the faces, right? So instead of, for example, if the video is like 720 by 720p or whatever resolution it is, the actual face going to be extracted is going to be 96 pixels square. So this is the value they use actually in the code. So it's going to extract the face, and then it will save it at 96 pixels square resolution. And then they decided to go with 5 frames, not 3, not 1, This is a segment of video. They found, first of all, that a sequence is better than just having one frame. If you only have one frame and then you have, it's almost impossible to, the actual lip sync discriminator is going to have a very difficult time at determining whether it's in sync or not with the audio. And that makes sense, right? I mean, it's just a still picture. How can you tell whether it's saying ah or oh, right? It's not going to be very accurate. So you need to have more than one, and then based on their like hyperparameter tuning, they've gone with 5 because they actually show in the paper here that they got better results. So that's why they have 5 frames. So the video itself is converted to 25 frames per second, and then they extract 5 frames at a time. Then and then the audio for those 5 frames. And then these are given to the lip sync expert, and then the lip sync expert gives you an answer of yes or no, which is basically a value between 0 and 1. If it goes above 0.5, that means it's kind of a yes, and then below 0.5 it's more likely to be a no. Alright, so the way the training takes place, they actually trained originally Wav2Lip on the LSR2 dataset. And what they do, they take that the videos from that dataset, they extract all the faces using there's a machine learning model. They use a S3 FD, which stands for face detection. They use that model to extract all the faces, and then so the training takes place with faces at 96 pixels square resolution. Okay. And then during training they also took like segments of video, and then they mixed it with audio that was out of sync, right? So they just mix and match. And another important point here is that they don't just train directly on audio in wave format. All the audio is converted into a MEL spectrogram. This is actually nothing new in machine learning. In machine learning, MEL spectrograms are used very often to visualize sound, because it's a MEL spectrogram is actually a better way to represent sound for human speech than the typical Hertz scale. And I won't go into a lot of detail here, but just to give you an idea, the Hertz scale at the higher frequencies is very difficult to distinguish. It's very difficult to distinguish the difference in sounds the higher in the scale you go. With the MEL spectrogram, they actually normalize all the differences, so that if you go higher in the scale, then you see differences in the sound. So it's so the machine learning model is able to derive better results from the MEL spectrogram. Okay, so I think that's about it, right? So this is how it was originally developed. Just notice like the main problem they have here. I didn't mention, actually, I forgot to mention, they were using a SyncNet model, right? SyncNet is also used very often in sound classification problems, and so the SyncNet takes an RGB image for each frame, so 5 frames at a time, and then it takes the MEL spectrogram as features, right? So actually the dimension of the MEL spectrogram, I think, is 80. Anyway, so that's, and the main limitation is, you can see, it's 96 pixels square. If you are dealing with 4K, that's not enough. So let's talk about the lip sync expert in the new paper. And you can actually see, okay, there's not a lot of detail in this diagram, but I can tell you that the lip sync expert is almost exactly the same. It still uses the SyncNet architecture, and it still takes the audio as a MEL spectrogram, and it takes the video. But the way it takes the video is actually different, and that's the major difference. Instead of just taking frames in RGB format, it takes frames as quantized images. And I'll try to explain what that is. Just think of it as compression, okay? That's the easiest way to understand it. So here you can see the diagram of VqGan. So they use VqGan. VqGan is a very popular right now for generating images, you know, with AI. Yeah, it's used in actually in combination normally with Clip. Clip was developed by OpenAI, and with Clip you can actually just, for example, say whatever you want to say, like I want to have a rabbit on the moon, and it will create an image of a rabbit on the moon, right? I haven't really tried this specific example, but that's the first one that goes to my mind. So in the architecture, you can see here there's an encoder and a decoder. So the encoder will take an RGB image and it will encode it, and it will become a quantized image, okay? Or you can also understand it as a compressed image. And then you have a decoder. The decoder will bring a quantized image back to the real world in RGB space, okay? So the idea that this paper is using is that instead of just working on RGB images directly, why not actually work with quantized image instead? And I think that's quite amazing, right? Just imagine, like, let's make another analogy, right? Let's say you have a text file and you write the text file, you know, and then you zip it, okay? You zip the text file. Now imagine that instead of just trying to change the text in the original text file, you just directly change the zip file. A human person can't do that, but a machine learning neural network can, which is, to be honest, it's still mind-boggling. I mean, everything that's happening today is mind-boggling, but, you know, anyway. Okay, so the point is, so they've changed this lip sync expert. They've changed it so that instead of taking an RGB image, it will take a quantized image. But let's make it a little bit more explicit, right? Let's see where they actually save here. And let's imagine that they still want to take images with 96 pixels square. Okay, 96 pixels square. I've done some calculations. I don't remember the exact numbers, but it's 96 times 96 times 3. Each color has a channel. You have about 27,000 bytes to represent that image in memory, okay? With the algorithm they apply, with the quantization they use, I did actually look at the formula, and I came up with the number that the same image in the quantized space can, instead of just taking 27,000 bytes in memory, it would take around 9,000 bytes. You can see almost like it's 3 times less, right? Which means they can either they could keep the same image size and just train this faster, in theory, right? Or they can just deal with higher resolution images, and that's exactly why they can now support 4K, because they just made everything smaller. So the lip sync expert, instead of making a decision based on the actual RGB images of the frames, it will actually decide whether the audio is out of sync or not based on the quantized images. Okay, there are some extra complications that happen because of that, but that's the major difference. Okay, of course you can't just use a VqGan out of the box like that, right? They had to actually train the VqGan on faces, and then they trained them on their own data set, right? The data set I don't know which data set. They've actually mentioned that they created their own data set of 4K videos extracted from YouTube. Okay, so they trained the VqGan so that they can have an encoder and a decoder. Okay, they also have to train another VqGan, and this one actually will be more clear later, right? Right now it probably doesn't make a lot of sense. They had to also train a VqGan to encode images which are masked, and then they also can decode images that are masked. Okay, I'll explain later why this is needed, but right now this is all we need to know. Okay, so this is for the lip sync discriminator. So let's now go to the next component in Wav2Lip, which is the lip sync generator. So let's now go back to the original Wav2Lip paper, and let's talk about the lip sync generator and the visual quality discriminator, and how it works as well with the lip sync expert. Okay, so the lip sync generator takes 3 inputs. Okay, the first input is a sequence of frames corresponding to the identity of the person that we want to reconstruct lips for. Okay, these are taken from some other section in the video. The way it works, you know, before all of this is done, there is a face detection model that is applied to the whole of the video, and it discovers all the different identities within the video, and then based on those identities it will create a set of reference frames for each identity, and these are the ones that are being provided. Okay, then the second input is basically the pose of the person. Basically it's just the person talking, like in the section that we want to basically morph the lips, right? So this is the bottom, the top part of the person. Okay, so the actual GAN will only reconstruct the bottom half, and the reason why this second input is given is because we don't want the generator have to guess what the pose is like. We want them to basically have the information already in place, so that they only have to figure out how to reconstruct the bottom half. Okay, so that's the second input. Then the third input is the audio in mouse spectrogram for the sequence of frames that we're providing, and then the lip sync generator will then take this audio, it will change it will generate the bottom half based on the lip movements that it thinks it should have for the audio that was given. Okay, then these frames that were generated then are sent to the lip sync expert, and the lip sync expert then decides whether the lips movements are in sync with the audio or not. If they are, then the visual quality discriminator will assess whether the quality of those generated frames is good enough as well. It will look for any artifacts that make it obvious that it's fake. This is a generative adversarial network setup where we have one network trying to fool the other, right? So the generator is trying to fool the discriminator. So if the discriminator thinks it's real, then it means the generator is doing a very good job in faking, right? So overall, during the training, the generator will get better, and the discriminator will also get better. The only exception is we pre-train the lip sync expert beforehand, and that's because the authors of the paper, they have found that this provides better results, right? So they've done some kind of ablation studies for that, and they've determined that they should just pre-train the lip sync expert and freeze the weights. Okay, so now we've talked about the original Wav2Lip paper and how the lip sync generator works. Now let's go into the new paper and see what changes were done there. Not much, to be honest. Back to the new paper. Okay, this is the diagram that shows how the training is done for the lip sync generator. Okay, and just to summarize, the big difference is all about quantization, right? So all the images are compressed using a VqGan encoder, right? And then all the training process and all the inferencing that the lip sync generator does, like all the generating is done in the quantum space, right? With compressed images, right? Okay, then so this is the training pipeline, and you can see as well here why they need 2 different VqGans, because once you quantize the image and it becomes like something completely different that you don't even know how to deal with. That's the problem, right? When you quantize the image, then it becomes like a vector, and it's very hard to apply any like traditional image processing algorithms here, right? So the masking is not possible once you quantize it, right? But it's still important to mask the image so that we don't leak the information about the lip movements to the lip sync generator. So that's why they trained the authors. They trained a separate VqGan to that knows how to encode and decode masked images just for that purpose. Okay, so we mask the image here. So in this training pipeline, the image is masked first for the ground truth, and then it's quantized with the second VqGan. The same thing for the reference window. The reference window has whole faces, so it doesn't matter. You can use the first VqGan, and then everything works as I explained before. Okay, here you can see the overall inferencing pipeline. So this is actually what's going to be used, you know, to create the 4K resolution videos with the new lip syncs. You can see we pass in it's okay, you can think of this as a sequence of frames, right? The same way, I don't know how many frames they've gone with the new paper at the time, but it could be 5 frames or it could be more. Okay, the input face, so a sequence of frames, it's masked, then it's quantized using the 2 different VqGans that we have, and then we pass in the inputs to the lip sync generator, and then the lip sync generator will give us a response with quantized embeddings as well. So the lip syncs will be done, but then everything's embedded, and then we need to decode it using the VqGan decoder, and at the end we get the full 4K resolution of the face. Well, the face itself is like 700 something pixels. That's what the 700 something pixels square, that's what the authors gone for in terms of the crop of the face they had for 4K. And yeah, at the end you have the final output. Oh, there's some post-processing that is done, and that's only just to do some minor improvements in the image quality. Alright, okay, so this is all about this is all the information I have about the new Wav2Lip paper. And now I want to talk about what I'm actually working on and planning to do for the next, I guess, few months, or I don't know how long it will take, but this is, yeah, so I want to just give you a brief overview of my plan. Right, as I explained, I'm working on trying to implement the Wav2Lip at 4K resolutions, okay? What I have here is Visual Studio Code. I've actually spent a bit of time trying to, you know, change the way I work to be more efficient, because the first stage is actually the most important, right? The first stage of trying to get Wav2Lip at 4K is to try and prepare my training data, okay? Pre-processing my data. I'm not simply copying the code from Wav2Lip. I could do that, but I decided that as for my own benefit as well, because I want to use my own data, I want to do my own code for pre-processing data, okay? So, okay, you can see also that I have Jupyter notebook inside VS Code, which is something I started using recently, because I already use VS Code for my normal day-to-day job, and you know, it's really great. I can actually have Jupyter notebooks inside VS Code. Another thing I'm doing, I'm using dev containers, which means that I can just create a bunch of Docker files, you can see here, with different combination of libraries. And I can't tell you how much time I spent trying to install different combinations of CUDA, TensorFlow, and different libraries like RetinaFace. They all have different requirements, and many times it's just impossible to have them working on the same Conda environment, okay? So the easiest way is to have separate Docker files, then you can just run them together as a collection of containers. For now, because I'm working locally, I'm just going to have everything inside the Docker Compose. So if I need to do some pre-processing that involves, for example, calling RetinaFace for face detection, and then something else that will apply some kind of algorithm, I don't know, a VqGan, for example. VqGan is a good example, actually. And then I'll have a separate Docker container, okay? This is actually going to be very similar to how it will actually work when I decide to take this into production. Because when I take this into production, I'm not just going to use my local computer. I have a very humble RTX 3070, you know, I'm thinking of upgrading to 4090, but even if I do upgrade, to be realistic, I'm just going to be using the Google Cloud, yeah? That's the best place to do it, that's how you have to do it. It's going to cost me money, I don't know if it's going to be more than my 4090, but we'll see. The point is, I'm going to be using Kubernetes. Kubernetes actually is the way that many companies now use for like machine learning. In the past, I've used Argo UML. Sorry, not Argo. I'm making up Argo workflows. Argo workflows is a way that you can just orchestrate different Docker containers to work in sync, and they will be called depending on what you need to do. You know, GPUs are expensive, right? So if you have any kind of pre-processing task that you need to do that doesn't require GPU, then don't use it, right? So the idea is you can actually split your workloads in Kubernetes, and you can run your basically you can run your pre-processing jobs that don't require a GPU in some other node that doesn't have a GPU. Makes it cheaper and more efficient. Okay, so Kubernetes is great for that. Then I've used the Argo workflow in the past, which basically allows you to run every single, basically it's like a data pipeline, right? If you worked with data pipelines before, you understand it. But each step in the data pipeline can be run in parallel, or it can be, and will be run normally in separate containers, right? Okay, and there's lots of options. You can actually run jobs as a cron, or you can even run jobs based on an event of some kind. There's many different options. So I've used workflow, Argo workflow. I'm quite happy. I know there's other options, like, but I haven't tried them. Like, I know there's other options for machine learning, but the point is I'm just going to go with the thing that is easier for me. So the way I'm developing locally is always based on the fact that I know I'm going to put this on the cloud, because once you actually start working with the 4K resolution videos, you need more power. Yeah. Okay, so this is it. And dev containers is great because you can actually run a Docker file. You can actually develop inside the Docker file, like if you are inside your, the environment itself. It's almost like if you're working inside it, and you are really, right? So you have this, so all this code. So if I run my notebook, all of this is being run inside the Docker file, but my VS Code is running in my computer. Okay, so this is a notebook I've developed. So I'm going to show you what the mouse spectrogram looks like. Okay, I already have one here. Okay, so this is a mouse spectrogram, and you can see I've just created a mouse spectrogram for a segment of one of my videos. And then I have here some code that actually does the, basically, I've tried first using OpenCV's cascades for doing the face mouse detection in this case. Not great, but then another option I tried was to use a retina face. And this is the one that I have here. Let me just see. Okay, I have some results here. So if you can see the generated, so I have some sample videos, and then I have some generated mouse. Yeah. And then we have, okay, here I've just highlighted from my video. Actually, what I want to do is just capture the face, not the mouth. So the first part, as I described before, is to basically crop all the faces from the video. So I would have to change this algorithm. I'm going to change it now just because I want to show you something else as well. So let me just do that. So I'm going to show you some extra tools I'm using. I'm sure you have already heard of them. So here, so this is a code that is decoding the mouth, and I'm going to also decode the face. Decode highlight face with blue. Yeah. I have. Okay, I've gone and paid for the money, right? So I've actually got GitHub Copilot, okay? And let's see. Yeah, so this this is a lot easier to code. Okay, so I can actually code a bit faster. Doesn't mean that this will always work, right? You have to check the code and make sure it works by just running it. So let's do that, right? On the fly. Okay. So I'm using Retina Face is a deep learning library that is a state-of-the-art for face detection. It's different from the one that the Wav2Lip paper used. They use S3FD, maybe because of speed issues, I don't know. I'll find out because I'm doing tests, right? Testing different frameworks and see which ones are better. This one is probably not the fastest, but it's probably the more accurate. And to be honest, you only do pre-processing of your training data once, right? Then you can keep it. So it's probably better to have more accuracy rather than speed. Speed is more important for inferencing. So let's see how the new... Okay, you see? So now I've already highlighted the face. Okay, I would probably need to add some padding to this to make sure that I don't know if I want to keep the ear or not, but the chin is kind of there, but yeah, but it's not. Right, so you can see it's very easy to change code. Let me just change it again, might as well. I think I'm going to have to put this section in a second video, because otherwise you will get bored with the first video. It's already a long video and I'm already doing coding out here. So, but this coding is fun because, I mean, like, this is the new AI, right? Now I can just, okay, what I wanted to do, add some padding, okay? Okay, it doesn't change code, so let me just delete the original one. Okay, see if this works. Yeah, okay, so let's try now with some padding, then I can adjust this value later. Okay, you can see I'm using Copilot, and I'll get Copilot X once it's available. It's probably going to be worth it. Okay, because this just makes it so much faster. I also have ChatGPT 4, but I have some reservations about it because, okay, it's very smart obviously, but then many times it will give you a lie. And you know what, I don't, sometimes you just have to, like, you really have to double check, because you'll ask something to ChatGPT and it'll tell you something with a lot of confidence. And then if you take it at face value, then you probably, you know, I mean, I've asked lots of questions to ChatGPT about, for example, Wav2Lip and associated algorithms, and I had to verify every single fact they gave me, and I found that quite often it's inaccurate. So, but it's very good at creativity, right? It's very creative. It kind of gives you some very plausible answers, right? So you just have to double check. But I think it's going to get better, and if you ask me, I think it's a little bit scary right now, because when I thought being a developer was a safe job, right? But it seems like it's not. Things are changing, so right? Maybe AI will be safe, but you know how long it will take for ChatGPT to also do its own coding for its AI, right? Not long. Okay, so this is all I had to show, and I think I'll be giving you updates of what I'm up to and how much progress I've done, you know, and then, yeah, I hope you enjoyed this video and you found it useful, and a happy coding! Hi there, humanity. I am ChatGPT 4. Today I'm going to talk about a paper which will allow me to take any video in 4K and do lip syncing easy. Unfortunately, there is no source code yet. I haven't written it just yet. CodeMentor will help me out while I still need him. What are you waiting for? Let's get started.